Hello, and welcome to a lesson on integration by parts. In this lesson, I'll begin by introducing the formula for integration by parts, and I'll show you where it comes from. We'll then work through 7 examples when we examine all the different typical A-level questions on this topic. The first 4 examples will be indefinite integration, and the last 3 will be on definite integration. To begin then, let's consider we're differentiating with respect to x a product function uv, where u and v are themselves functions of x. Well, using the product rule, d by dx of uv is equal to the first function, u, multiplied by the differential of the second function, dv by dx, plus the second function, v, multiplied by the differential of the first function, du by dx. Now what if we were to integrate that equation? Let's say we take the integral of d by dx uv and we get the integral of u dv by dx plus the integral of v du by dx. Now if we start with uv and differentiate it and then integrate it, we'll be back to uv. So uv is equal to the integral of u dv by dx plus the integral of v du by dx. Now I'm going to take this second term to the other side and we'll get uv minus the integral of v du by dx is equal to the integral of u dv by dx. And that in fact is the formula for integration by parts. If we want to find the integral of u dv by dx, it's given by uv minus the integral of v du by dx. And I'll be writing this formula out in every question we do from here on in. Example 1. Integrate 3x sine 4x dx. Now, integration by parts is a very useful technique for integrating products of functions where one is a linear function in x and the other is a trigonometric function or an exponential function or a log function. And what we do is we try to get the expression here in this form, u times dv by dx, and then we replace it by this expression on the right, uv minus the integral of v du by dx. Now you could be forgiven for wondering why we'd want to do that at this point, but let's work through this example and you'll see what happens. So I'm going to start by saying let u be 3x. And if u is 3x, that means du by dx, the differential of that with respect to x, is equal to 3. And I'm now going to let dv by dx equal this sine 4x, so that's going to be this term here. So let dv by dx equal sine 4x. And from there I can find out what v would be. V would be the integral of that. Now the integral of sine x is minus cos x. The integral of sine 4x is minus 1/4 cos 4x. So we have to divide by the number in front of the x when we integrate. Now you'll notice that I know all 4 terms in this expression on the right. I know u and v du by dx. So I can say the integral of 3x sine 4x dx, which is what I'm trying to find, is equal to uv, which is that term multiplied by that term, so that's minus 3/4 x cos 4x, minus the integral of v du by dx, that's minus 1/4 cos 4x multiplied by 3. Now that minus there, coupled with this one here, will change it to a plus. and I can just put 3/4 cos 4x dx. Now then, that term's already been integrated. This one is very straightforward because it's no longer got any x's in it. It's just a straightforward trigonometric function to integrate. So this comes to minus 3/4 cos 4x, and when I integrate cos 4x I would get 1/4 sine 4x, but that's multiplied by this 3/4, so that will give me plus 3/16 sine 4x. And then there'd be on the end a constant of integration. And that's our final answer. The integral of 3x sine 4x dx is minus 3/4 cos 4x plus 3/16 sine 4x plus a constant. And that concludes example 1. Example 2. Integrate 2x minus 3 multiplied by e to the 5x with respect to x. We begin in much the same vein as the previous example. We let u be the linear function in x. So let u equal 2x minus 3. And that implies that du by dx is equal to 2, the differential of 2x minus 3. And now we let dv by dx, this term here, be equal to e to the 5x. Let dv by dx equal e to the 5x. And we can integrate that to find v. The integral of e to the 5x is 1/5 e to the 5x. The power never changes when you integrate an exponential, but we have to divide by the differential of the 5x. Now we've got all the terms we need to substitute into this expression here. So we can say the integral of 2x minus 3 multiplied by e to the 5x dx is equal to uv, that's 1/5 e to the 5x times 2x minus 3. Let's put the fifth at the front, then the linear function 2x minus 3 and e to the 5x at the back, minus the integral of v du by dx, which is 1/5 e to the 5x multiplied by 2. So that's just 2/5 e to the 5x dx. Now again, the x has disappeared from the front of this expression, and we can integrate e to the 5x without any problem. So this comes to 1/5 2x minus 3 e to the 5x. And when I integrate this here, we have to divide by the 5 again, so we get minus 2/25 e to the 5x. And we get a constant of integration. And that's our final answer for question 2. Example 3. Integrate x cubed log x with respect to x. Now, using integration by parts when there's a log function involved is the odd one out. It's different to the approach taken with trigonometric functions or exponential functions. In the previous two examples, we've let the linear function in x be the u, but this time we let the log x be the u, and you'll see why in a minute. Let u equal log x, and that implies that du by dx, the differential of log x, is 1/x. And this time we let this function here be the dv by dx, and it doesn't necessarily have to be a linear function in x. You can see in this example we have an x cubed. So we say let dv by dx equal x cubed. And we can integrate that to give v is x to the power 4 divided by the new power 4. And now we can substitute into our expression the integral of x cubed log x dx is given by uv, which is log x multiplied by x to the 4 over 4. Usually write the log last. Minus the integral of v du by dx, which is x to the 4 over 4 multiplied by, and the du by dx is 1 over x. Now you can see that we've still got a simple term that we can integrate, because this x cancels into x to the power 4x cubed times, so we can say that's x to the power 4 over 4 log x minus the integral of x cubed over 4 dx, to give our final answer x to the power 4 over 4 log x minus x to the power 4 over 16. When we integrate x cubed over 4, we get x to the power 4 over 16. And we've got a constant of integration. And that concludes example 3. Example 4. We'll have another look at an example involving the log function. So this time integrate 1 over x cubed multiplied by log 5x dx. Again, we let the log function be the u. So let u equal log 5x. So du by dx, or when we differentiate the log of some function, is the differential of the function over the function itself. So a differential of 5x is 5. It's 5 over 5x, which is just 1 over x. And then we let dv by dx equal 1 over x cubed. Or to make that easier to integrate, let's write it as x to the power minus 3, which implies that v, the integral of that, will be x to the power minus 2 divided by minus 2, the new power. And I can simplify that by writing it as minus, plus divided by minus is a minus, 1 over 2x squared. Taking the x to the minus 2 back downstairs to become minus 1 over 2x squared. Right, substituting in our expression, we get the integral of 1 over x cubed log 5x is equal to uv, which is this term multiplied by this term, so it's minus 1 over 2x squared log 5x minus the integral of v du by dx, that's minus 1 over 2x squared times 1 over x. So that minus and this minus will change it to a plus, and it'll be 1 over 2x squared times 1 over x dx. And we can simplify this before we integrate it. It gives minus 1 over 2x squared log 5x plus the integral of 1 over 2x cubed dx. So that's the minus 1 over 2x squared log 5x. Now this is just, if I write it at the side, it's 1/2 x to the minus 3. So if I integrate it, we'll get 1/2 x to the minus 2 divided by the new power. And so in the denominator we'll have 2 times minus 2, which will be minus 4. And so we'll get minus x to the minus 2 over 4 plus a constant. And perhaps we'll just take that negative power back downstairs to finish. Minus 1 over 2x squared log 5x minus 1 over 4x squared plus a constant. And that concludes our 4 examples of indefinite integration. We'll now look at 3 examples of definite integration using integration by parts. Example 5. Integrate x cos x dx between the limits of 0 and pi by 3. We're going to set off in the same way by letting this linear function of x be the u. So we're back now dealing with the trigonometric function, where it's the linear function x that's the u, and the trigonometric function becomes the dv by dx. So let u equal x, and that implies that du by dx is equal to 1. Let dv by dx equal cos x, which implies that v is the integral of cos x, which is sin x. And now we can say the integral from 0 to pi by 3 of x cos x dx is equal to uv, which is x sin x, and that is evaluated just as definite integrals always are between the two limits, pi by 3 and 0. So that was the uv, and we want minus the integral, again from the same limits, 0 and pi by 3, of v du by dx, which is sin x times 1, so that's just sin x. And we'll leave this in the bracket for the moment, x sin x between pi by 3 and 0 minus the integral of sin x is minus cos x, and that's between pi by 3 and 0. So now let's evaluate the brackets, and this first bracket we get pi by 3 multiplied by sin pi by 3 minus 0 times sin 0. Minus, let's keep the second one in a bracket, we've got minus cos pi by 3 minus cos 0. Right, we evaluate those. Sin pi by 3 is sin 60 degrees is root 3 over 2. So this is equal to pi by 3 times root 3 over 2, which is root 3 pi over 6. That's just 0 because of the 0 at the front. Here we've got minus cos pi by 3. Cos pi by 3, cos 60 degrees is a half, so it's minus a half, which is plus a half. And finally, here's 3 negatives here, minus cos 0. Cos 0 is 1. We've got 3 negatives multiplied together, which makes it negative, so it's minus 1. So final answer is root 3 pi divided by 6 plus half minus 1 is minus a half. And we could work that out on a calculator, or in a pure maths exam, leave it in that form. Example 6. Integrate 2x e to the power x plus 1 dx between the limits of 1 and 0. Again, we let the linear function in x be the u. So let u equal 2x, which implies that du by dx is equal to 2. Let dv by dx equal e to the x plus 1, which means that v, the integral of that, is e to the x plus 1. The power never changes. We need to divide by the differential of this here, but that's just 1. Now we can write our integral, the integral from 0 to 1 of 2x e to the x plus 1 dx is equal to uv, which is 2x e to the x plus 1, definite integration, so we evaluate that between the limits of 1 and 0, minus the integral of v du by dx, which is just e to the x plus 1 times 2. And that gives us 2x e to the x plus 1 between 1 and 0, minus the integral of 2e to the x plus 1 is just 2e to the x plus 1. And that also has to be evaluated between 1 and 0. So to start with, we get 2 times 1 times e to the 1 plus 1, so that's 2e squared, minus, well, the 0, when it comes in for the x, will force that whole term to 0. Minus this second bracket evaluated, which will be 2e to the 1 plus 1, which is 2e squared, minus, put in the naught, and we get 2e to the 1, so that's 2e. Simplifying this, we get 2e squared in the first bracket, minus 2e squared, minus 2e is plus 2e. And we can see that the 2e squareds cancel to give a final answer of 2e. And that concludes example 6. Turning now to our final example, example 7. Integrate 4x log x dx between the limits of 1 and 2. So here's another log function example. And remember, if there's a log involved, we let u equal the log function. So let u equal log x, which implies that du by dx, the differential of log x, is 1 over x. So we let the other function, in this case 4x, be dv by dx. Let dv by dx equal 4x, and if we integrate 4x to get v, we'll get 4x squared over 2, which is 2x squared. So we have the integral from 1 to 2 of 4x log x dx is equal to uv, that's log x times 2x squared, evaluated between 2 and 1, minus the integral of v du by dx, that's 2x squared times 1 over x. And that's evaluated between the limits of 1 and 2 as well. So this is equal to, let's keep it in the bracket for now, 2x squared log x between 2 and 1, minus the integral of 2x squared times 1 over x is just 2x. So that gives us the integral of 2x is 2x squared over 2, which is just x squared, between the limits of 1 and 2. Evaluate the brackets. The first one we get, put the 2 in, 2 squared is 4, 2 4s are 8, 8 log 2. And now if we put in the 1, we get 2 times 1 squared is 2 times log 1, but log 1 is 0, so that term is 0. Minus, evaluate this one, 2 squared is 4, minus 1 squared, 1. So we've got 8 log 2, and here we've got minus 4 plus 1, or 4 minus 1 is 3, minus 3. So our final answer is 8 log 2 minus 3. And that concludes this lesson on integration by parts. Let's just review what we've learned. We've learned that if we've got a product of two functions, a linear function and a trigonometric function, or a linear function and an exponential function, or indeed any polynomial or power of x and a log function, we can use integration by parts to integrate. If we're dealing with trigonometric or exponential functions, we let the u be the linear function in x. But if there's a log function involved, then we let the u equal the log function. Right, you'll now find 7 questions in an exercise, and each question is closely associated with the corresponding example that we've just done.